अच्युत शंकर प्रभृतिभिः देवैः सदा वन्दिता सा मां पातु सरस्वती भगवती निःशेषजाड्यापहा। शुक्लां ब्रह्मविचारसारपरमाम् आद्यां जगद्व्यापिनीं वीणापुस्तकधारिणीमभराम् जाड्यान्धकारापहाम्। हस्ते स्फाटिकमालिकां विदधतीं पद्मासने संस्थितां वन्दे तां परमेश्वरीं भगवतीं बुद्धिप्रदां शारदाम्।
Thank you, sirs. Please have your respective seats. Galileo Galilei once said, "A ship in port is safe, but that is not what ships are meant. They are meant to sail and explore new horizons." This reminds us that true progress comes from stepping beyond our comfort zones in pursuit of growth and achievement. To advance, we must reshape our thinking and welcome fresh perspectives. This national conference on frontiers in theoretical and experimental physics sets sail on the voyage of scientific exploration, charting unknown waters and expanding the limits of human understanding. The theme of the conference is to review main developments of theoretical and experimental physics. During the theoretical sessions, we will cover topics like quantum technologies, astrophysics, nonlinear systems, and nuclear physics. While the experimental sessions will focus on the areas like material science, high energy physics, and radiation physics. We will also be understanding the applications of these areas in industry and medicinal research. The conference promotes interdisciplinary collaboration and including discussions on biophysics, and it emphasizes the importance of synergy between theoreticians and experimentalists. Over the 2 days, experts will discuss challenges and developments in their research. It provides opportunities for collaborations, career advancements, and scientific networking. This will serve as a platform to bridge the gap between scientists, academics, and young researchers. Additionally, it will offer postgraduate students and even undergraduate students an exposure to advanced research methods. The conference includes keynote address, invited talks by the eminent resource persons, oral and poster presentations by the researchers as well as students. Before starting, we are honored to welcome Dr. Mukesh Kumar as our chief guest for the inaugural session of the conference. Dr. Mukesh Kumar is an esteemed professor in the Department of Physics at Indian Institute of Technology, Roper. I would now like to invite all the respected dignitaries on the dais to please come forward and present a token of our heartfelt gratitude to our chief guest of the day. Sirs, please. Please clap. Thank you, sirs. Along with Dr. Mukesh Kumar, we also are honored to welcome Dr. Sunil Bansal, who is an assistant professor of physics at UIET Punjab University, Chandigarh. I would also like to wish our heartfelt welcome to him. Thank you, sir. Now, I would like to invite our convener of the conference, Dr. Umar Raji, to please come on the stage for the formal introduction of the chief guest of the day, Dr. Mukesh Kumar.
Respected Principal and Conference Director, Dr. Rajesh Kumar, the Chief Guest of the day, Dr. Mukesh Kumar from IIT Ropar. It was called Upcoming IIT Now. It has already developed fully, and they have a very big physics department over here. Dr. Sunil Bansal from UIET Punjab University, Chandigarh. Overall DBT coordinator, Dr. Puneet Puri, who happens to be head of zoology department also. Dr. Sunil, Dr. Ritu, all the faculty members, teaching and non-teaching, and my dear students. Our endeavor is always to bring the best of the best speakers with whom you can interact. The conferences are made to develop your contacts and to get ideas what is happening all around us in the field of research in physics. When we used to attend conferences, we used to have new connections. We used to talk to those speakers. We used to get motivation. Yes, I can also do it. And from there, you also get the ideas. So your effort should be, if you are attending conference not for the sake of attending because you have registered, try to meet these speakers after they give their lecture. You can also meet them during lunch time or during tea time, and from there you can get idea. You should have questions. If you don't have questions, you will not be able to go higher. Those who have questions, only they go high. So Dr. Mukesh Kumar is a professor in the Department of Physics, IIT Ropar. He did his MTech and PhD in physics from IIT Delhi. He worked as a postdoctoral fellow in the National Renewable Energy Laboratory, USA, from 2010 to 13 on nanoscale charge transport of organic solar cells and flexible thin films for next generation flexible optoelectronic devices. Before joining IIT Ropar, Professor Kumar was working for Hesitron Inclination USA. Professor Kumar has published 2 book chapters, 10 review articles, and total more than 80 research articles in peer-reviewed journals. Professor Kumar has received many national and international awards like Young Scientist Research Award from Department of Atomic Energy India, Bhaskara Advanced Solar Energy Fellowship from Indo-US Science and Technology Forum, Faculty Research and Innovation Award IIT Ropar. Recently, he received JSPS and prestigious Fulbright Nehru Academic and Professional Excellence Fellowship from Japan and USA. Professor Kumar is a selected member of Indian National Young Academy of Science, National Academy of Sciences, India, and Fellow of Institute of Physics, UK. Recently, Professor Kumar developed a prototype device and won the first prize in India by Ministry of Defence, Government of India. His research interests include functional and renewable energy materials for optoelectronics and voltage application. It deserves a big round of applause from all of you. And we should be thankful and grateful that he has spared time to join us and interact with our students and research fellows. Thank you so much.
Thank you, sir, for introducing our chief guest of the day. Now it is my distinct pleasure to invite our visionary principal and conference director to deliver formal welcome address for the delegates and attendees. Our principal, sir, has been an inspiring leader and driving force behind this conference, and he has demonstrated a steady commitment to foster innovation and excellence in the college. Under his guidance, this conference has come to realization, bringing together a diverse group of participants eager to engage, learn, and participate. I welcome you, sir, on the stage to share your wisdom and vision and officially commence our event. Please, sir.
Thank you very much, Dr. Sunil. It gives me immense pleasure to welcome our chief guest, Dr. Mukesh Kumar, Professor, Department of Physics, IIT Roper. Alongside, we have Dr. Bansal, Sri Bansal, from University Institute of Engineering and Technology, Punjab University, Chandigarh. He is also one of our speakers in one of the sessions. Professor Kumar Rajiv, Head Postgraduate Department of Physics and Conference Convener. Dr. Puneet Puri, DBT Coordinator. Dr. Sunil, Dr. Ritu, Organizing Secretaries of this prestigious two-day conference. Faculty members, and very dear students. It gives me immense pleasure to welcome our guest speaker today. He is a very widely experienced, widely read, and very acclaimed researcher in his chosen field of physics. Professor Kumar Ji read out his lofty achievements in various areas, his research credentials. He is member of so many professional bodies, and above all, what I was observing that he is an IITian by training. IITian by training, that he did his MTech as well as PhD from prestigious IIT Delhi, and now he is faculty at IIT Roper, which is again very promising and upcoming IIT among the new IITs which have been established in the country. Dear participants, this 2 days national conference on frontiers in theoretical and experimental physics. We started it last year, and this time we are having the second season or the second version of this conference. Last year when we organized this conference, we got very overwhelming response from all quarters. We got research scholars and postgraduate students and teachers from more than 5 states of North India. So this encouraged us to continue this venture, and this year the department organized this conference, and to my surprise, this year we have participants from more than 8 states. This again, it speaks that this conference was a roaring success last year, and we are ready to do better this year. Dear students, the field of science is very vast, and what we understand science today, there is a long history, there is a long contribution of scientists of the world as well as of India. There are so many scientists in India in the field of physics, chemistry, mathematics, life sciences, and space sciences who have done tireless efforts. Though their journeys were not easy, because at that time, when they started working on science, there were no facilities. The people, they were not very aware. There was paucity of funds. But during those trying times and under hard conditions, they made us understand the science what we understand it today. So their contribution is immense. If you take the name of Dr. C.V. Raman, so he was a great physicist. He worked on fundamental physics. He was a Nobel laureate for the Raman effect. And to commemorate his discovery, we celebrate National Science Day every year in the country on 28th of February. And thereafter, Dr. Homi Jahangir Bhabha, he is the father of Indian nuclear program. He's also instrumental for establishing this nuclear program because he was a nuclear physicist, and his contribution in the nuclear program, particularly nuclear energy for peaceful purposes, that is remarkable. So he also worked under very hard conditions, and Bhabha Atomic Research Center, Trombay, in Maharashtra, that is successfully running and working on atomic energy. Then we have Dr. APJ Abdul Kalam. He's called Missile Man of India. So he was a scientist par excellence who became later on President of India also, and he was a space scientist. Then nobody can forget the name of Dr. Vikram Sarabhai, the person who is after the space program of India, Mission Moon, Mission Mars, so many missions what you talk about today. It is basically the contribution of ISRO that he established. He not only established ISRO, he established IIM Ahmedabad also, and he also established Tata Institute of Fundamental Research. That's again a very prestigious institute that he was instrumental in establishing. Then Dr. Jagdish Chandra Bose, J.C. Bose, though he was a physicist, but he worked on plant sciences also. He was a biologist, he was a botanist, and he worked on wireless communications. As botanist, he was the first person to tell that plants, they have feelings, they have life, and he proved it experimentally. Thereafter, there are a few more names, like Dr. Srinivasan Ramanujan. He was a mathematician, and he's known for his the magic with numbers because he worked with number theory. Then Stender Nath Bose. Stender Nath Bose, he worked with Albert Einstein. Though his work was not recognized much, but his contribution in the field of science is immense. Another person is P.C. Ray. Praful Chandra Ray, he was a chemist. He laid the foundation of inorganic chemistry, and he was instrumental in the development of chemical and pharmaceutical company in Bengal. He wanted that cheap medicine should be prepared in India, and our dependence on the foreign medicines that should be minimized. Then another physicist, Meghnad Saha. So Meghnad Saha, he is also considered among the top 10 scientists of India, and he was a practical physicist, and his main work was thermal ionization theory that completely changed our understanding of the stars. Then another scientist who was a Nobel laureate, Dr. Hargobind Khurana. Though he was not a physicist or chemist, but he was a biologist. He was an Indo-American scientist who was awarded Nobel Prize. And all these people, they have worked under very stress conditions, very hard conditions, very trying conditions, and they have brought the science to the present form that we understand it today. Dear students, at present we have so many institutes that you can choose from for your study as well as research. But earlier it was not so. Now it is difficult for us to make a choice of good institution because there is a long list of research institutes and education institutes across India. I'll just tell you few of the institutions which you can choose for your scientific this research, like Aryabhat Research Institute of Observational Sciences, Nainital. This is an institution which deals with astronomy and astrophysics. Then Bose Institute, Kolkata, it deals with the multiple fields of physics. Then BARC, there's a Baba Atomic Research Center at Mumbai. It deals with atomic sciences and nuclear physics. Then we have Indian Institute of Astrophysics. It's again at Bangalore, dealing with the astrophysics. Then Indian Institute of Space Science and Technology, Trivandrum. Institute of Physics, Bhubaneswar. It deals with the condensed matter, nuclear and high energy physics. Institute of Plasma Research, it is at Gandhinagar. It deals with experimental and theoretical physics. Then Jawaharlal Nehru Center for Advanced Scientific Research, Bangalore. It again deals with experimental and theoretical physics as well as condensed matter and material science. Then Physical Research Laboratory, Ahmedabad. It deals with theoretical physics, solar physics, space research, planetary and geosciences. Then another one is Raman Research Institute, Bangalore, that deals with astronomy, astrophysics, light and matter physics, soft condensed matter physics, and theoretical physics. Then TIFR, Tata Institute of Fundamental Research, it's again at Mumbai. It deals with astronomy, astrophysics, condensed matter physics, material science, high energy, nuclear and atomic physics. Then we have IISc, Indian Institute of Science, it is at Bangalore, which is a nodal center for research in science, engineering, design and management. So these are some of the top class research institutes dealing with different aspects of physics in practical and theoretical aspects. That's what the theme of the present workshop is, this conference is, that is Frontiers in Theoretical and Experimental Physics. Apart from this, the students, they are free to choose from ICERs, Indian Institute of Science, Education and Research. There are 7 ICERs in the country. We have 23 IITs. Again, in the IITs, there are excellent centers of research in physics and other sciences. There are then NITs, they come next in the hierarchy. We have 31 NITs in the country, and then central universities. In India at present, we have 56 central universities, and in all the central universities, you will find the physics as a main department where the research is conducted. And then we have, of course, 495 state-funded universities, what we call as public universities. And in all those universities, we have these departments of physics where you can pursue your higher education as well as research. So dear students, this conference where you have come, it is just an ignition point. It is not the end, but it's the beginning. You will develop contacts with the people. You will come to know that's what's happening in your field and what field is best for you. Because these conferences, they act as a platform where we exchange our knowledge, we exchange our views, what type of research we are conducting, how to write research papers, and many more things. So we are going to have almost 6 invited talks here on different fields of physics, and all those speakers, they are coming from very reputed institutions and they are established names in their fields. So I convey my best wishes to the organizers. They have made this conference happen for the second time, and we pray that this practice continues, that every year the Department of Physics at DAV College Jalandhar organizes this conference on frontiers and this experimental and theoretical physics every year. So we'll make it a feature. So once again welcome our guest speakers and thank all the participants. I wish you a comfortable stay for these 2 days. Thank you very much. All the best.
Thank you, Principal Sir. You have set the tone for the next 2 days of our conference. Sir, I would like to bring into your kind notice that we have received participants from the ICERs as well as NITs and central universities across India. So it is your continuous guidance that we have achieved this feat under your leadership, sir. Thank you, sir. And now, before, without making you wait for some other time, Now I would like to invite our chief guest and keynote speaker of the day, Dr. Mukesh Kumar, to please come forward and shower his ideas on the participants. Thank you, sir.
So, cheers. Thank you, sir. Okay, thank you. Yes, please. Very good morning, and thank you very much for the kind invitation. I'm really organized to come here. And first of all, thank you very much for the festival and for the invitation. So, I'll discuss about the research that we are doing here in IIT Roper. And I'm a teacher, so you can stop me at any time if you have any confusion, so I will not mind. So what we discuss actually about the three films and microstructure for solar blind photo detector. Okay. So I hope my voice is clear, right? Okay. So we discuss about thin films. So thin films actually is a layer, continuous layer of very low thickness, which is very less than even the human hair. So the human hair thickness is about 80 micron, and this total device thickness is less than 1 micron. So that is 100 times lower than the thickness of the human hair, the complete device. And that is the magic of the nanomaterials and thin films. And all of your device, all of your cameras, your mobiles, all these things at least contains thin films in one or another form. That is the main gate actually of IIT, and you know that actually this IIT actually is there in the Indus Valley civilization. So all these remainings actually is carved on these 4 gates, and these actually symbolize the symbol of technology. So that is a simple cubic structure, 8 atoms at the corners, and we are actually building that on top of our tradition. Okay, so first of all, actually, I would like to acknowledge IIT Roper and all these funding agencies, and as well as actually is DBT here because they is providing actually funding for this conference. And so this is actually what we are doing in IIT. So what we are doing actually, we are working on different aspects of the thin films. So what we are doing actually, we are working on this thin films which is transparent and conducting as well. So as you know that actually metal are conductors. However, the glass that transmit the light is insulating in nature. But these are the special kind of material which is conducting as well as transparent in nature. And one of the layer actually is in the one of the most loved things for your life is your mobile. So one of the layer actually is contained there, so that allows the light to come to our eyes, and then it also like when you touch, so it also change the capacitance. That's how actually it's multi-interactive devices and the displays are work. So we work actually is one of the layers. Also we are working on the 2D materials. So that is layer material actually is having a thickness of about 1 to 1.5 nanometer. And these materials are special because they do not have any dangling bonds. So you can thin down any material at nano level, but once you thin down, then you have the dangling bonds, which is leftover bonds, and they react with the environments. That's why their stability is not good. But these materials do not have dangling bonds out of the plane. So these devices actually is very stable. And now you have heard about the 2D machine, 2D mission of Government of India, and it is just launched, but it's officially not announced yet. The Government of India has planned to invest about 1,000 crore rupees only for these 2D materials based devices for futuristic application. And other thing actually that we work on this solar cells, so that is like earth-dependent solar cells. And this is the topic actually that I will discuss today is about the solar blind photodetector. So what is solar blind photodetector? So the photodetector is any device that is converting the light into the electricity. Okay. And this kind of a photodetector is a special photodetector because that is only sensing a particular spectrum of the solar spectrum. Right? So we will discuss about that in details. So what are other thing actually that we are working? So this is the tungsten conducting oxides that we are working. Right, and then this is actually, as I mentioned, that these are the high electrical conductivity and high transmittance, and this is the intersection where these tungsten conducting oxides are working. And we are like mainly contributing for the development of these flexible thin films for the next generation flexible optoelectronic devices. So when you are saying that why the mobiles are not flexible yet, because it has many challenges. So one of the main material that is comes for the mobile fabrication is the chip which is made of silicon, and silicon is not flexible; it is brittle in nature. Also, the other material that is comes for the coating is also not flexible in nature. So that is actually we are developing one of the layers that is actually flexible in nature, and if you bend it, actually it will not lose its conductivity. The other thing actually we are working on the solar cells. So these are the things actually that we are working on the solar cells. So I mainly actually discuss about this solar blind photodetector. So what we will discuss about the solar blind photodetector? So I'll discuss about what are the current challenges and what the material we are working on for the solar blind photodetectors. And these are the things that we are trying to conclude, and we will see actually how far we reach. So first thing first is fundamental. What is photodetector? So the photodetector, actually the best photodetector is the human eyes, right? So whatever the light is coming in all visible spectrum starting from 400 nanometer to 700 nanometer, we can sense it with a different wavelengths. And not only that, the literature says that human eyes can sense a single photon. So the sensitivity is very high, and also we can sense it the different wavelengths as well. So whatever the best technology available is not even able to meet the nature. So whatever actually we are developing, we can sense only few wavelengths, like one wavelength or two wavelengths. But human eyes can say actually that this is the blue color or this is the red color, right? Even the girls can distinguish more color than the man, right? So that is what is the shade of the colors. My daughter actually teach me, no, this is not that color, this is that color. Okay, so I learned that from her. So that is actually human eyes, and then you can sense that light in the different colors. Okay. And what we are doing with this, though we are shining the light, and this is my material which is absorbing the light, and that semiconductor is converting that incident light into the electron and holes. Now I separate these electron and holes, and that is my electrical signal. So I am sending the light, and then I am detecting the current out of that, and then try to mimic that how far we can reach. Now, why this special kind of photodetector is important? Why solar blind photodetector? Now, if you see that the light coming from the sun, it contains whole spectrum, starting from your IR and beyond that, microwaves and all, and then the visible light that is coming from 400 to 700 nanometer, and then we have the UA, UVB, and UVC. The UV and UVB actually is good for the body absorption where the vitamin D actually is produced, but the UVC actually is very harmful. and it causes skin cancer. And if you have the mother nature actually provide us the ozone layer which absorb the radiation coming. Radiation is completely absorbed by the mother nature, so there is no UVC radiation present on Earth, right? And then when you are having this UVC radiation, it can cause the skin cancer, which is really not good. And you know that actually just to avoid this, the sun exposure to the skin and it is damaging the skin, you know that we apply the sunscreen lotion, which nothing but the contains zinc oxide nanoparticles and some vitamin C and other supplements which absorb this UVC light and do not get damaged the skin, right? But if you have the UVC light, that is actually really bad to the skin. So once there is no UVC light, if there is no hole on the ozone layer, then why we are working on this photodetector? In ideal condition, there is no UVC light on the atmosphere. Then why we are working on that? We are working because the other source of the UVC light that is coming from the plume of your missile or maybe fire, it is acting as a signal for the UVC light. And since there is no UVC light coming outside the atmosphere, so even a very weak signal of UVC light can be easily detected. And that's why actually the sensitivity of this photodetector is very high. And their application is starting from the civil to the military application. So that can actually track the missile as well as it can track the fire actually that we have in the isolated locations. So you can track this UVC light by using this photodetector very easily. Now this is actually the application of this photodetector. So you can actually sense the hydrogen flame, and you know that actually hydrogen is one of the dangerous gas because more than 4% of the hydrogen gas ignite itself. Don't need anything in the atmosphere. So that's why actually if you have the hydrogen, so hydrogen is a clean fuel. It burns with mixed with the oxygen and give the energy, lot of energy and the water. That's why you might heard about the hydrogen cars and all this. But the problem is only the storage, because we cannot like just sit on the kind of a missile. It is a big cylinder of the hydrogen, and then you are driving your car. It's highly dangerous. So it can act as a sensor for hydrogen gas because hydrogen gas actually when it burns, it's not visible to human eyes. So it can, since this fire actually will have some part in the UVC light, so you can easily detect that. So you can see actually this is the propane flame and this is the hydrogen flame. This is completely invisible. However, it is visible in the UVC region, so that it can detect actually by using these materials and these photodetectors. Now, what are the other applications? Actually, is a ozone hole monitoring. Suppose there is a big hole in the ozone layer, you can monitor that. It will be used. It used actually as a unit sterilization, missile tracking, flame detection, space exploration, and drone line of sight communication. Now, as for the old devices, actually these devices also have some parameters that need to be characterized or quantify what is the performance of these photodetectors. The first thing is the responsivity, that tells you what is the amount of current produced per incident power of the optical the light. So that is given by the IPS, that is current, and then divided by the optical power, that is sine. So that unit is ampere per watt. Now the next one actually is the external quantum efficiency, which tells actually the number of electron hole pair generated and collected divided by the number of incident photons. And then we have the linear dynamic range. The dark current is the current which is producing on by the device when there is no light sign on that. And then we have the response. That means if you shine the light, how fast it is detecting that. It is in the microsecond or the nanosecond or even millisecond. And then we have the persistent photoconductivity. That means when this light is shined, so it will immediately increase the current. And when you turn off the light, how fast it is going to the base level. So that is also critically required. There is a possibility that the photodetector will give the current and then it is slowly reducing with time. So there are many materials that reduce their current in months and years. That is not required. So these are the other parameters like the dark current, response time, specific detectivity. All these sense actually how fast this photodetector can work. Now you should ask the question like silicon is already there in the periodic table, which is one of the most studied element in the periodic table. All the devices are made of silicon. Then why we are not using silicon? Because the band gap of the silicon is 1.1 electron volt and corresponding wavelength will be about 1100 nanometer. That means it will sense 1100 nanometer and shorter than all the wavelengths. And 250 actually is much shorter. So that means it will absorb all spectrum starting from 1100 nanometer to all the way to the shorter one. So this photodetector will not have the sensitivity specific to UVC light. So either we have to use the filter that will filter out all this radiation and you will have only UVC light. But utilizing that filter actually is a big challenge because that increase the bulkiness and also that degrades with time. Another material actually that you can have the aluminum gallium nitride that you can tune the band gap of this material by mixing the gallium. But if you mixing the aluminum in the gallium oxide more than 40%, that increase actually the strain and the higher dark current actually is there. However, the other material actually have their own limitation, including the diamond film, which has a high band gap, which is about 5.5 electron volt, and that is giving the shorter than the UVC light. So these are the challenges. Actually, the silicon is not good, so we utilize the gallium oxide, which is one of the good material because it's a direct band gap material, and then it is intrinsically solid line. So band gap exactly match with the UVC light. You don't need any kind of a filter or anything. And that is ideally for high thermal stability because of this high temperature, and then high chemical stability and high breakdown field, which is required for high power devices, which is one of the another application of this material. So I'm not going into detail about that. So we are working on all these aspects for this gallium oxide for solar blind photodetector as well as power devices. These are the different polymorphs of the gallium oxide. So you have this alpha, epsilon and gamma, but the beta actually is a more stable phase, and if you read all these, so it will convert into the beta gallium oxide phase. Now, what are the challenges of the gallium oxide? It's not like you have discovered something and then it's easy to go. Gallium oxide have its own challenges, and the challenge of the gallium oxide is difficult to draw p-type. Okay. So now you can see actually this is the energy and K diagram for gallium oxide, and you can see actually the flatness of the valence band. So when the valence band actually is flat, that means it's difficult to draw with p-type. You can have only n-type coupling, and that's why we cannot make p-n type of the devices of this material. It has a poor thermal conductivity, so high temperature utilization of that is not good. And there is always trade-off between the responsivity and response time. So absence of that p-type actually we can go for unipolar devices or the charge separation by utilizing the other method, because whenever this light is absorbed, creating an electron hole pair, we need to separate them easily. Otherwise, they will recombine and then they will not produce the current. So what are the other way actually? So we can have this kind of a device. So you have the gallium oxide, and then you have the substrate, and then you can have the same type of a contact. So when you have the same type of a contact, the problem is you will not have any restriction for the flow of electrons. So electron can easily go from one side to another side. So it will have very high dark current. However, we should have actually some kind of a like barrier here, so that electrons should not go from here to here unless until you apply some voltage. Okay, so it's just like a water barricade. So you lift the side so that the water should not go on the other side unless until you overflow that. So what are the other way actually that we can get? So that is the Schottky barrier height you can make. So that means a different type of a metal, because the metal different type will have a different work function. So that there will be electric field. So whatever this carrier will be generated because of this electric field, they will sweep out. And or we can have the metal semiconductor metal type of the contact, or we can make the heterostructures of this gallium oxide with another type of the material which already exists in literature having the p type nature. So this is actually the literature that is summarized what is being done actually already in the literature. So that is the amount of current produced by incident power, and this is the response time. That means how fast it is acting and what is the amount of current it is producing per incident power of the UVC light. And you can see actually this region is still empty. Why it is so? Because you are not getting actually fast speed of this photodetector, and the responsivity actually is still lagging. However, the silicon, if we are talking about the already commercialized device, which is very fast, having a response time in nanosecond, but the responsivity actually is very poor in the UVC region. So that is also a limitation of the silicon-based photodetectors. So to meet all these challenges, we start working actually on these materials and how to achieve all these goals. So first thing actually is all this work is done by all PG students, and their PG students actually is coming from all around India. Starting from like many students coming from Punjab University and some local colleges. So don't worry about your future in basic science. Okay, so I was just discussing with your head of the department, the principal. You might have initially that there is no future in basic science. I am standing in front of you. I did my MSc and then we did my MTech and PhD from IIT Delhi, and then I work in the best to best institute in the US. Okay, we certify the solar cell efficiency around the globe, and then I was working in a company in the US. I had a green card there. Okay, but once I got offer from IIT, I come back immediately because I need to serve my country. Okay, so it's not like basic science do not have a future. Basic science have a future, but it requires dedication. Okay, so don't feel actually small. Basic science have the future, but it requires more challenges and it requires actually more time and more dedication. So this student, so this she is a Kanika Arora. So she is a student from very small college from Meerut, and now she work actually in one of the top institute in the world. She is in Harvard University. Okay, she is doing postdoc there. Now that is actually first work she did, and now this work actually is highly cited. So if any people working around the globe on gallium oxide, they recognize us because of the work doing by our student. Okay. So my main motivation here is not to bore you with a lot of results and this. So if I am able to motivate even a single student today in the conference, that will be success to me. So what we have done here, so that is actually the growth. So what we are doing actually for growth, so we are having a solid target of a gallium oxide, and now we are making a film. How we can make a film? So film actually we can make by condensation. Condensation actually, you know that if we create a supersaturation means like if we take a glass of water, put a 1 spoon of sugar and dissolve it, it disappears, right? Because the sugar particles goes in the between the space of the water molecule. Now if you put one more spoon of the sugar, it disappears. One more, you will have some part in the bottom. So that means it reaches to the limit. But if you add one more spoon of the sugar and little bit increase the temperature, the sugar will disappear because it increases solubility. Now if you bring this solution at room temperature, now that solution has more amount of sugar that should have at room temperature in the solution. This solution is known as supersaturation, right? And that happens almost for 2 months in Punjab, right? When during the mid of December to January, when there is a fog. And you have seen actually the foggy nights and days, right? So that is just nothing but the supersaturation of water. Because in the night the temperature goes down, the water vapors remain same, and then the water's amount is more than it should be at that temperature. Now you have the supersaturation. And now if this supersaturation solution is come in contact with any sharp thing like branches of the trees, then what happens? It's just like a rain-like situation under the trees in the foggy night, right? So we use the same concept. We create the supersaturation, and then we put a mist of water the trees. So we put a substrate, and these vapors condense on this substrate and make a very thin film, depending on the time of the exposure. Clear? So this is the temperature, because this material actually is having a high melting temperature, is about 1800 degrees centigrade. So we heat the substrate and then keep the temperature lower than the melting temperature. So that is a 650 degrees centigrade. So that these vapors which is created can condense on that, and it gets a sufficient time so that it crystallizes. Okay. So this is the things actually different like kind of a planning how we can crystallize that. Now these are the just how to see actually the material form. So we utilize atomic force microscopy, which is to see the things at the nanoscale. Okay, and then we see that, and this is the XRD which is used to see the crystallography of the material, whether it is a polycrystalline, whether it is a single crystalline, or whether it is a amorphous in nature. And then we observe that in one particular condition we start to get the peaks. So that is signifies that it is a polycrystalline in nature, and this is amorphous in nature. And you can see the total length of this side actually is 5 micron. So you can see the particle size is very small, of tens of nanometer. And this root mean square roughness is very small, for that is about 0.3 nanometer, that means 3 angstrom. Now this is actually is the final device is formed, and then we made the contact by using optical lithography, and you can see actually this all this the length, width, and all this. And this is the system actually control system in the lab to test all these photodetectors, because we want to shine the known amount of the light on the photodetector, and then we will detect the current by using the precision teethless source meter. Okay, so these are the contact actually we make. So the one contact here, another contact here, and then we measure the performance of this photodetector. So this is the current versus the voltage, and then you can see actually that this is with the wavelength. So that means this is 600 nanometer to all the way to 200 nanometer, and you can see actually this photodetector is working only in the UVC light, and it's not detecting any other wavelength in any other region. So you can see that. So this is 600 nanometer, and then this is 250 nanometer. So that means the photodetector is only detecting the UVC light and not any other light. Now we want to see actually when you shine the light, the current should increase, right? So it should have the reproducibility. So then we tested that. So that is actually you can see that. So if you zoom in here, so that is the kind of a pulses source. So it is going up and down, up and down. So whenever you are shining the light, then it is current is increasing, and then when you removing that, this is going to the background. So after the light actually is removed, photodetector should go to the same baseline. So this is not required. So this is the optimized one. This goes to the same background, and then the current actually remains the same. And that is actually so this is the mechanism for that. So I'm not going to do that. So this photodetector that we have made actually is compatible as per the photodetector available in the market. So the photodetector that is available in the market is either actually from the Thorn lab or from the silicon or the diamond, and their performance, whatever we get inside the lab, is much better than the photodetector available in the market. Now, how much time I have? So now actually this is the thing like we want to grow that silicon gallium oxide on different type of the silicon. So how many of you are here from the physics background? MSc? Right? MSc? Okay, that's good then. So you understand actually what is the silicon, different planes, right? So now if you are sitting here in the room and I can consider that origin, and then if this is the x-axis, y-axis and z-axis, so now you know actually where is the 100 plane, right? So x-axis, so that wall is 100 plane, right? If I consider 11 plane, so that will be the wall which is connected to the this edge, right? And the 111 plane will be the three doors connecting from this to that to that. So this will be triangle, right? So these are the different plane and how we achieve it. So we have the single crystal silicon and we cut that according to their crystallographic direction, and that have the different arrangement of the atoms in the different planes, and that have the different surface energies, right? So the surface energy now, if you are having a different type of silicon here, and then I put the gallium oxide on top of that, so this gallium oxide will choose one of the optimum orientation of the silicon. So we want to study which orientation is good for the growth of the silicon, the gallium oxide. So we have done that. So this is actually atomic force microscopy, and we analyze how this is changing. So we observe that for a 111 plane, which has the highest density of the atoms, lower surface energy is better for the growth of gallium oxide, and that is actually giving a better performance to us. So these are the actually straight calculation. So the end result is that the performance of this one silicon 111 plane, that is grown gallium oxide, is much better than any other of the plane. Now this is actually spectrally selective. So when I'm talking actually human eye, so you can see the red, blue, green, yellow, all these colors, right? But the device that is available in the market, they are not smart enough. It's like you can absorb the light. Like suppose silicon is there, silicon band gap is 1.1. That means corresponding to 1100 nanometer, right? So you can absorb 1100 nanometer and shorter wavelength because that is in the higher energy. But it will not distinguish that whether it is 1100 nanometer or 500 nanometer. It will produce the current, but it will not tell you that which light is coming to the photodetector. It absorbs and creates the electron hole pair. You cannot distinguish any two lights. You can only distinguish the two wavelength when you have the two materials, right? So when you have the material which absorb 1100 nanometer, once you have a material which absorb 300 nanometer, then only you can distinguish two wavelength. So we here to try the two distinguished wavelength, and now you can understand how complex is the nature, right? So here we utilize the plasmonics. So we utilize the silver nanoparticles and coat it on the gallium oxide and try to distinguish UVA and UVC. So for that, what we have done, so what we have done actually, we have the gallium oxide. On top of that, we coated this silver nanoparticles, and you know that all these metals show the plasmons. Plasmons means if you shine the electromagnetic radiation, they oscillate and then re-emit that light, and they have strong absorption that corresponding to their the frequency. Okay, the plasmon frequency, and for that the plasmon frequency actually comes in all about UVA region. So once you made the photodetector out of that, so you will realize that this is the gallium oxide, simple gallium oxide, and then once you light the UVC light, it is showing 0101. However, the gallium oxide, when you shine the UVA light, it is not showing anything, and it should not show because the wavelength is more than it actually it should absorb. But if you have the silver nanoparticles on top of that, which is absorbing 400 nanometer light, then it is showing the performance for UVC light because it is absorbing corresponding to gallium oxide, but also showing the response to UVA light because it is absorbed by the silver nanoparticle and injected to the gallium oxide. So for better understanding, we can see that when the UVC light is shined on top of gallium oxide, it creates electron hole pair, and then the current comes out. When this silver nanoparticle is there, when you shine the 400 nanometer, then this hot electron is ejected from the nanoparticle and it reaches to the gallium oxide, and then it is flowing, but the direction of the current is reverse. Now I can understand actually which wavelength is coming, because it is showing me the different response for the different wavelength. Now that is actually the this very fascinating result. So that is a flexible kind of photo detector. So the one day actually one student come to me that, sir, why we are using silicon, we can use simple paper. I said no, that is not a good idea. सिंपल पेपर अगर हम यूज करते तो लोग यूज कर चुके होते। तो स्टूडेंट ने बोला नहीं सर, वी वांट टू ट्राई। ओके, I never stop student unless until you do not break anything intentionally in the lab. You are free to do whatever you like. So what they have done here, so now you have the simple, the flexible actually we want to draw. So now you have the simple paper. Okay, so you have the simple paper, and if you see the optical microscope, then you will see actually the paper is kind of a flakes, right? They are interconnected to each other, and then what we have done, we took that paper and we have taken the pencil, the HB pencil with a high darkness, because that is graphite, highly conducting. So we made an electrode on the bottom, and then we put that inside the chamber, high vacuum. We coated the gallium oxide layer on top of that, and then we again actually made a top electrode, and now your photodetector is ready. It's out of paper actually, it's ready. Now you can do whatever you like. You can twist, you can bend, it's a paper. But there is a problem. Problem is that our aim actually is to put it here, and then we just see that whether how amount of the UVC light is being exposed to your skin. But the problem is whenever you put that on the skin, then the sweat will damage that, because the paper will absorb the water and the device will be damaged. So to overcome that, so that is a student actually Kanika Arora. So what she did actually, she paint the nail paint on the photo detector so that it is transparent. So and then actually it is repellent to the water. So they initially that works, but then I asked actually don't paint the transparent nail paint. We ordered some special kind of a transparent glue which is water repellent, as well as like it is good for the use with the devices. So this is actually the optical microscope image of that, and then you can see this is the electrode and this is the channel of the device, and this is the performance of the device, and that's actually you can see actually performance is very well. Okay, and you can twist it, bend it, whatever you do, actually the device is still functional. Now what we have done actually, so we try to see that because we want to quantify, we cannot say that sweat is coming and then the damaging, how fast it is damaging. So what we have done actually, we put a water droplet on top of the paper and try to measure the contact angle, because when the water will absorb, the water contact angle will reduce. Okay, so we try to measure that, and we observe within the 60 seconds the water is kind of absorbed and it is damaging the device. After that, actually you put the paint on the both side of this paper, the device, then we observe actually there is no damage. The device is actually perfectly contact angle is same. And now before and after, this device actually is working. And the beauty of that is because we put the asymmetric electrode. The bottom is graphite, top is silver, so they have the different work function. You do not need to connect the battery; it works by its own. So you see actually the applied bias is 0. You just need to communicate this with your mobile, and it will give you how much UVC your skin actually is being exposed. And then once you are done, so you can just burn it, and that's it. It's a completely green, very cost effective solar night photo detector that can work as an indicator of your exposure for the UVC light. So that is actually we studied. Another thing is about the two-dimensional materials. So we have tried different combination of these materials. So since the time actually is less, so I will just focus on some of the very important data. So now, once we are planning to use this device for a missile tracking application, so we need to maybe mount this device on the missile itself or somewhere in the harsh environment. So we want to study that whether this device is stable at high temperature or not, and what is the upper limit of the stability of the temperature. So to study that, what we have done actually is a simple study. So complete device which has a gold contact on that, we simply hit with that, and we want to study when it fails and why it fails. So you can see actually that, so this is the gold electrode, this is the gallium oxide, this is silicon, and this is the optical microscope, image. So this is the room temperature which shows no damage. At 450 degree centigrade, there is also no damage, but 650 and 850 degree centigrade, the black dots are there that shows actually the devices start to degrade. Now to understand that microscopically, what we have done, we try to remove the atom by atom whilst we are going in the depth, and we try to understand which element actually is coming on top. So we observe that at 850 degree centigrade, the gallium from the gallium oxide films even reach to the top, and that is causing the failure of the device at 850 degree centigrade. So that means the device is still working at 650 degree centigrade temperature, which is very high in comparison to the nitride devices. So this is actually all about the X-ray photoelectrospectroscopy, right? So this is the spectroscopy used from the basic principle of photoelectric effect, for which Albert Einstein got the Nobel Prize in 1921. Okay, so another thing actually we use another type of the material. So just this is a transparent conducting oxide, not a conventional metal, and this is the special material. And we also study the same, and we observe that this material actually is very specific and very useful actually for instead of the conventional metal. So all these things actually again we use the device against the still heavy ion, because if you want to use that device in the outer space, then you have to study how much ions actually is incidenting on your device, and that may cause the radiation damage, right? So all the satellite and all these things we are sending, we study that if a device is exposed to that much amount, then it will be damaged or not, or what will be the changes in the device. So to this experiment actually be done at IUAC New Delhi, and this high energetic ions of 120 MeV or 100 MeV is signed on these fields, and then we try to understand what is the failure, why it is failing. So this is the scanning electron microscopy image of the control device, and you can see for the amorphous and the polycrystalline films how it is changing, and we observe that the amorphous film actually is much better than the polycrystalline, because it is already in amorphous stage, and when the radiation sign, the performance actually is even better. We even actually against the lowering the performance. So you can see actually here the responsivity and the emitting temperature. So you see that 250 degree centigrade indeed the performance is much better than even the control device, so which is improving the performance of the devices. So that is actually the summary of the work. So we are working actually in gallium oxide, this is ultra wide bandgap materials for the UVC photodetectors, and trying to study its interface and the heterostructure for its usability for UVC detector that has many applications including missile tracking and in the defense and the civil area. By doing actually all this work, so we participated last year in one of the contests, and we got actually first prize in India for the prototype development, and we received that prize actually by our defense minister last year. So this is actually, as I mentioned, I'm just presenting the work. Okay, so this work actually is completely done by all PhD students. So I have about 10 PhD students, 2 masters, 2 BTech, and 1 postdoc. They're working in the lab, and all these students come from the rural background. okay, from small colleges. The dreams, and then maximum you will see actually are the girls. In my lab, in out of 10 students, 8 are girls and 2 are boys. Okay. So all these students are working in good universities. So the students actually up to this, they are already graduated. So she is working in IT Bombay. She is working in Zurich. She is working in Poland. She is working actually as assistant professor in Noida. Okay, and he is working in Switzerland. She is actually as I mentioned, actually she is in Harvard. He is working in Italy. Okay, and he is a BTech student. He is also working in USA. Okay, so all these students, and these are most of the students are placed in very good position. So don't be shy. Choose the career in the basic science, but you have to work hard. ये नहीं है कि हाँ अरे वो मेरा साथ वाला तो उसने कुछ लिया था ब्रांच, वो उसका तो प्लेसमेंट हो गया। अरे प्लेसमेंट हो जाने तो उसका प्लेसमेंट 20-50 हजार क्या हो गया? आपका गोल अलग है, योर विजन इज डिफरेंट। ओके, सो चूज द कैरियर, डोंट बी हेजिटेट इन द बेसिक साइंस। एंड विद दैट, थैंक यू वेरी मच, एंड इफ यू हैव एनी क्वेश्चन आई एम हैप्पी टू आंसर। Any question, please don't hesitate. I always say in my class, question is never stupid, answer maybe. Yeah, please.
Minimize dark current at high temperature.
Yes, it's a very good question actually. So, if you increase the temperature, the origin of the dark current actually is the amount of current flowing without light. And if you see actually in the different materials, you have the heterostructures and you have the barrier at the interface. Now the problem actually that the carriers is getting higher energy and they try to escape. So to minimize that, we can have the interfacial engineering. So between the metal and the gallium oxide, we can have another material of very thin layer which is actually more thermally stable, like Al2O3. So we can put that, and so that the carriers has to cross like large amount of barrier with the like minimum amount of kind of a voltage they will able to cross, but with the thermal energy they will not be able to cross. So in that way actually we can minimize the dark current, but dark current actually high dark current is one of the killing factor for the device. It reduces the sensitivity. Because if you are flowing microampere current in the dark and you are getting actually very small amplitude, the delta, when you are shining the light. So the dark current should be as low as possible.
That dark current, better separation, better to achieve it band gap tuning.
Better to
Achieve it band gap tuning.
band gap, it is not the band gap actually, this is the interface. So I do not focus actually there. So you can see actually review of the band alignment. Okay. So like here, right? So this is one type of the material, gallium oxide, and then if you have another type of the material, now the electron actually is going from this side to this side, so they have to cross this barrier. Right? Now if it is actually this kind of an alignment, now if it is reaching little bit high, then it will be difficult for the thermal carriers to cross this barrier. So that is the interface engineering that you can do to reduce that to some extent. But dark current is always there. We can minimize it, and our goal actually is to get it maybe somewhere in picoampere. So the one of the best thing actually that initially saw the dark current we achieve about a few picoampere. Now if you have the light, once you shine the light, and if your current actually is coming in microampere, now you have 6 order of magnitude increase, right? Now if your dark current is increased, but your still light current is there, then delta will reduce. So that responsivity actually will reduce. So that is mostly decided by the defects at the interface. But now since you are actually asking, so another problem is the interfacial defects. So the defect plays very critical role. It is responsible to increase the responsivity and also it is responsible to reduce the response time. Now you have to optimize that. What is the max optimum point? Because these defects is doing actually they are capturing the one of the carriers and then another electron actually keep on circulating unless until this force is released. So we realize that actually when you are signing the photon, so we are getting many electrons corresponding even if we have signed actually one photon, we are getting large number of electron hole pair. And you should ask actually then from where this electron hole pair coming, right? So this is the optical gain. It's because of the defect. Now if you are reducing the defect, the responsivity will reduce, but it will increase the response time. So response time may go to nanoseconds, but responsivity will reduce. But if increasing the defect, it will increase the responsivity, but it will slowly. It is just like a road में अभी इतना गड्ढा हो गया, right? So गाड़ी तो slow जाएगा, but गाड़ी slow जाएगा, right? So that is the problem. Response time will reduce. So these two parameters are really critical: response time and responsivity. Simultaneously, both of these parameters cannot be achieved at very large extent.
Professor, it was a nice talk. My query is like you are telling about the XTL plane. So have you ever compared with the other directions also, like 100, 010? Why 11 only? So
Okay, so the silicon that we get from the industry, there are three preferred cut is 100, 110 and 111. So now if you are asking the industry that you need 211, they will not supply because these are the three cut actually available. Now we want to see the variation in the surface energy and there is a huge variation in all three substrate direction. So that's why actually we selected 100 or 110 and 111. But the different other cut actually is like suppose sapphire. You can get actually suppose Z orient, C oriented sapphire or other direction. But cut direction HPL depending on my wish is not available in the market.
like when we transport making a defect creating in the system. How you manage the defect?
Yes. So that is actually controlling the defect to some extent is possible, but thermodynamics in the nature lies the defect. Okay, like in diamond, we have the defect. Nature want to have the defect. It is very difficult to grow a single crystalline film in comparison to polycrystalline. Nature wants to have some bare minima. Nature amorphous भी नहीं चाहता. Nature single crystal भी नहीं चाहता. Polycrystalline easily grow हो जाएगा. Okay, so we can minimize the defect. So especially for gallium oxide, we can minimize the defect. The main defect is there is oxygen vacancies. So while we are creating the plasma, once we are growing the film, we introduce the extra oxygen in terms of the activity which is in the plasma. So the oxygen goes and then fill the oxygen vacancies, and then we have the stoichiometric gallium oxide. But achieving the stoichiometric gallium oxide is not fulfill the goal. As I told you that if you reduce the defects, it will reduce the responsivity. Response time will better. So we have to optimize somewhere depending on the application.
When we show the report, it's a vertical or in plane?
That is vertical.
So when we specialize is also in the experimental way, also start from the both layers.
Yes. So that is actually this interface is grown. If it is grown at room temperature, there is a least chance that the both interface is mixed. But we want that interface should be mixed a little bit, about few nanometers. That helps to send the carriers very smoothly. जैसे दो रोड होते हैं ना, दो रोड पे जब कनेक्ट करते हैं आपने देखा होगा जो पैच होता है वो बिल्कुल ऐसे स्मूथ नहीं होता है 80 किलोमीटर पे गाड़ी आसानी से जाती है राइट अगर दो रोड दोनों स्मूथ हैं और दोनों ऐसे हैं तो क्या होगा इस abrupt right you cannot drive so we want that the interface should be smooth and then it is like at the same level so what we do actually we anneal little bit about 250 degrees centigrade so that this at least few layers are intermixed each other to make a smooth kind of a junction, auto junction for the carriers. And there are many studies actually where the people intensely create defects at the interface so that it increases the responsibility. Good question is coming. Any other question? Yeah, please.
Figuring out by wearing the D in the two layers, one we increase in the if we change the D, so much in the distance, as a give for separation, so maybe then this study means
D means
when we vary the equidistance D, this also changing the structure and external properties also. People have reported.
oh, interplane spacing.
Yes.
Oh, that means actually different material.
Not like for people also reporting on the airport, but they actually vary the D. These are the standardized D. The gap is there. They also like varying the increasing or decreasing. So the way they actually
So that actually if you change that, so it will create stress at the interface. And it
the
is,
actual miles.
yes, so that is actually, so it's just like you have the layer actually. So if you are bending like this, so it is kind of a tensile here and here actually it is compressive, right? So depending on the lattice parameter which is on the plane, the top layer can be managed. It will be either tensile or compressive and that is one of the way actually to engineer the mobility. Because the mobility actually, if you study, the mobility is a depending on the effective mass. And the effective mass depends on the second curvature, the curvature of the EK diagram. Right? So it is h square square by double derivative of EK diagram. So if you have very sharp and then very shallow, it depends on the mobility. So you can change it and then mobility will change. So there is a well-known actually, it's called the strain engineering. Strain MOSFET. So time actually strain silicon MOSFET. So people assume the mobility increase manifold and the performance also increase many times. So this is one of the way actually the strain can be managed and strain engineering actually is so important that it is a separate branch in the physics, the material science. The people apply the strain and not only on the conventional film but 2D materials. So if you apply the strain on 2D materials, it changes many things. Many exciting things appears. Like acetone lifetime will change, acetone separation will change, carrier separation will change.
In your case, professor, can you make it how you manage to lesser electrical resistance because from increasing the photoconductivity?
Okay, so the resistance actually, as I mentioned, the resistance will be decided what the minimized defects as per the gallium oxide is highly insulating in nature. But it always is the intensity and type because it always has some oxygen defects, oxygen vacancies and gallium interstitials, always have. So if we supply large amount of oxygen while it is growing, then it increase in resistance manifold. So when you make a contact, measure the current will come in femtoampere, right? So that's why actually we can increase the resistance, but it, as I mentioned, actually we have to achieve somewhere optimum because increasing the resistance too large, you have to select the electronics that can measure the current in that range, right? I want to measure the current so that it can measure the current in the field. I don't want to bring there my quickly 420, which in itself actually is 50 lakhs, right? I will say actually I will apply some resistance and then voltage. So the current is coming converted to the voltage and then it will be some signal. So there is always some optimum where we can supply some oxygen and then little bit reduce the defects so that the conductivity comes in that way so that my current is in the microampere also. It should be sub microampere dark current so that my current is comes in the ideally milliampere.
So, any more questions? Participants, we are already lagging behind the schedule. So, if you have any question, you can interact with Dr. Mukesh during the break. So, thank you, sir. Your session was very insightful and informative. And participants also made that interactive also. We, as organizers of the second national conference, acknowledge your efforts in doing your work and hard work you have put forth in making your work and also spreading your knowledge on others. Thank you so much, sir. So now it is the time for a tea break. Let us take a break of around 15 minutes, and after 15 minutes we will again gather here. Meanwhile, the participants who are going to present their oral presentations, they might check their oral presentations over laptop over there. So let's take a break of 15 minutes and strictly 15 minutes only. And the participants, after checking your presentation over the laptop, they can visit lab number 2 for tea break. Thank you.